Okay, everybody, good job doing the questions from the textbook. Now I'm going to give you the answers. Here they are, and then I'm going to explain them to you so you can pause the video so you can see these. We're just doing this. And then here are the others, 9 through 20. Now if you need an explanation, here it is. All right, so number 9. First thing that we do, of course, is we write out everything. So if you're struggling, right, great problem solving strategy, you just say, Q1. All right, so Q1 is equal to -2 times 10 to the -4th coulombs. Q2 is equal to 8 times 10 to the -4th coulombs. And R, the distance between them, is 0.3 meters. After this, it's really just plugging the numbers in. So you've got F equals K Q1 Q2 over R squared. All right, so our numbers. K is 9 times 10 to the 9th. Q1 is 2 times 10 to the -4. Q2, I'm going to run out of space, 8 times 10 to the -4 divided by 0.3 squared. So that's it. You can't really see that. Okay? Plug that into your calculator. Be careful when you're plugging things into your calculator because sometimes you hit divided by, make sure that the squared is going to this. You can hit the E button, 9, and then there's the double E there, E9, 9E9. And so the answer is -1.6 times 10 to the 4th newtons. Okay, number 10. So this is pretty straightforward. They give you these numbers, you put them in here, and you're done. Number 10 is a little different because here they're giving you the force and they're asking you to find the distance. So Q1, they tell you, is -6 times 10 to the -6th coulombs. The force is 65 newtons, and the distance is 0.05 meters. And they want you to find the other charge. And so it looks like this. We start with F equals K Q1 Q2 over R squared. Does it matter which charge we use? No. This could be Q1, it could be Q2. It doesn't matter. So you pick whichever one you want it to be. Now, I highly, highly recommend that you solve this first, then put the numbers in. The fewer times you have to do a calculation and some arithmetic, the less chance there is that you're going to make a mistake. Do the algebra before you put the numbers in, unless there's a number that's 1 or 0. 1s and 0s make things disappear, so we put them in. But other than that, we're going to wait. All right, so I'm trying to get Q2 by itself, so I'm going to multiply R squared to this side, so F R squared equals K Q1 Q2. Now I'm going to divide both sides by KQ1, because I'm trying to get that by itself, so over KQ1. So Q2 is equal to FR squared over KQ1. And now, again, it's just a matter of putting in the numbers. So this is 65 newtons, R 0.05 squared. K is 9 times 10 to the 9th. And then Q1, -6 times 10 to the -6th. Plug that onto the calculator and you should get -3 times 10 to the -6th coulombs. All right. 11 is a follow-up to a sample problem that they did. So on the previous page, there was a sample problem, and there are 3 charges. There's charge A, charge B, and then there's charge C. Charge A is +6 microcoulombs. B is -3 microcoulombs, and micro means 10 to the -6, by the way. And then this is +1.5 microcoulombs. Okay, so what they do is they solve this. Now this is being pulled this way, by this, and it's being pushed up by this charge. These are opposites, so it's attracted that way. These are the same, so it's pushed away. So the net force, right, if this is A, the net force on A is something like that, F net, in the sample problem. Here, they change this, right, and so it's a little different. C stays the same, but this becomes positive 3 microcoulombs. Right. Because the numbers are the same, the magnitude of the force does not change. The magnitude is still whatever it was before. I didn't even write it down. But the thing that's different now is the direction of the force. Now, I'm not going to ask you to calculate that direction, but if you wanted to try, it's just trigonometry. If this is, here's A, so particle B now is pushing on A that way. So here's the force of B on A, and then C is pushing this way, and it's a little bit less. So here's the force of C on A. And what you would do then is you would take, this would be your horizontal, your vertical component, and you would make a right triangle out of it. So actually you'd put this here, this here. And so this is the net force on particle A. It's in that direction, right? So this would be horizontal, vertical. You could do Pythagorean theorem to get this, and then you could use tangent to get the angle, or inverse tangent, I should say. But again, you don't have to do that. So just know, so the answer that you need to be able to get is simply that this is the new direction of the force up and to the left, and the magnitude is the same as before. All right, number 11. Number 11, they give you a whole setup. You have an axis, and A is at the origin. So here's A, and A has a charge of 2 times 10 to the negative 6 coulombs, and then 2, 4, 6, 8. Here's particle B. B is negative 3 times 10 to the negative 6. Or sorry, negative 3.6. And then particle C is 4 times 10 to the negative 6 coulombs. This is 0, this is at 0.6, and this is at 0.8. This is 0.4, 0.2. And if you didn't do this, make sure you do this in the future, draw the diagram. Drawing the diagram is going to help you so much to visualize this and understand it. So make sure you do that. Okay, and now it's just a matter of finding the net force on this. So we find the force of B on A, so we find the force between these two. Then we find the force between these two, and then we just add them up. So this is kind of like, this is negative, so you can imagine somebody, B, is pulling on A that way. C, these are both positive, so C is pushing on A that way. So you get someone pulling, someone pushing, and then you're just trying to find what's the net. So you take this amount and you subtract the other amount. So A looks like this, the force diagram for A. Here's the force of B on A. Here's the force of C on A. Okay. So then the force of B on A, I'm going to calculate this, is just going to be K, so 9 times 10 to the 9th, times 2 times 10 to the negative 6th, times the charge of B, negative 3.6, times 10 to the negative 6, over 0.6 meters, that's the distance, squared. And this comes out to 0.18 newtons to the right. Okay, and then here the force of C on A, got 9 times 10 to the 9th, 2 times 10 to the negative 6th, times 4 times 10 to the negative 6th, over 0.8 squared, and this comes out to 0.1125 newtons left. So we put these two together, right? This is 0.18, this is 0.1125, and you end up with 0.0675 to the right. This is the net force, newtons, I should say. This is the net force on A. That minus that is the net force. Number 13, now we want to find the net force on B. All right, so I'm going to leave this because this is, according to Newton's third law, the force of B on A, right? You just switch these. So this is the same. It's just going to be left. Right, so now if we're looking at particle B, here's B. Right, it's pulling. A is pulling on B that way. Here's the force of A on B. Force of C on B, these are both positive and negative, so C is going to be pulling, but it's a lot closer. So this is probably going to be a much greater force this way. Force of C on B. Oops, I lost that. So now I got to calculate this, the force of C on B. Here's the force of B on A. I've already done this. Oops, sorry. Let's see. A on B. Now, force of C on B. 9 times 10 to the 9th. Negative 3.6 times 10 to the negative 6th times 4 times 10 to the negative 6th over 0.2 squared. And this does come out to be much more. It's 3.24 to the right newtons. And so then you put these two together and you get 3.06 newtons to the right. And that's the net force on particle B. Right? And then we're on to these other questions. How does the force relate to the charge? Well, if you have more charge, then you have more force. It's that simple. Opposites attract and likes repel. 15. More distance, less force. If you want to be precise in the way that you say it, you can say that it's an inverse square relationship, just like gravitation. And then if you triple the distance, you'll have 1/9 of the force. Right in here. If this is tripled, then the overall force is going to be 1/9 because you have to square that. And we saw a bunch of sample problems like that in the lecture from last week. 16. The leaves, they'll go out a certain distance, and then they'll be held there because gravity is pulling down. There's still that gravitational force pulling on those leaves. And there's going to be a balance between the gravitational force pulling down and the electrical forces that are pushing outward on that electroscope. 17. If you have something that's positive and you want to charge something else positive, you just touch it, and it'll transfer some of the charge. But if you have something positive and you want the other thing to be negative, then you do that charging by induction and grounding. So you get it close, so all the positives go away, and then you touch it, so all the positives go to something else. You let go, and now you have something that's overall negative. And again, we saw something like that in the video from last week. 18. So why is it that neutral things can be attracted to anything? Like, for example, when you put the balloon against the wall in the simulation, the wall is neutral. But what happens is that the negatives, so it's not a metal, but the electrons can still move a little bit. Things can become polarized. Become positive on one side, negative on the other. And because of that, because the atoms and the electrons can move a little bit, and the fact that opposites attract, that's why neutral objects, overall neutral objects, can be attracted to either positive or negative. 19. If you're charging something by induction and then you ground it, but then you take away the thing that's charged, then whatever left and went to ground is now going to come back to the thing. Right? So the knob, if you leave the wire attached, grounding the knob, you put something near it, you take it away, it's not going to make any difference. The stuff will go to ground and then it'll come back because everything is seeking to be overall neutral. as long as it's not in the presence of anything else that's charged. And then 20, Newton's third law. So the force on one is the same as the force on the other. The magnitudes are the same, but they're in opposite directions. Very simple, just like we saw here for this one. Okay, so I hope that answers all your questions. Let me know if you have any other questions. Now you got to make sure you submit this and then take the quiz. And hopefully we'll see you soon.